Welcome back to the series. Let's recap our journey so far. We started with the naive implementation. It was incredibly fast but completely broken because of race conditions and memory reordering. In the last video, we fixed it using a mutex. It was safe, but it was super slow because thread had to sleep and wake up. In today's video, we're gonna reach the final goal using atomics. We are going to build a queue that is both safe as well as fast. We do this by manually controlling memory barrier. Let's begin. We start in the producer thread. Just before we need to know where to write, we load the tail index. In the mutex version, we would have locked the mutex. Here in this version, we just load the atomic variable using a memory order relaxed. Why relaxed? Because only the producer writes to the tail. We don't need synchronization just to read our own nodes. It just adds overhead. So we are proceeding with memory order relaxed. Now we check for space. We compare our next slot against head. This is our first barrier. In the naive video, this is where we risk reading a stale value and overwriting unread data. The acquire shield guarantees that if the consumer has updated head, we definitely sees it. It syncs up with the consumer's timeline. Now we have space. We write data to the buffer. Pay close attention to this visual. See how the data is ghosted and dashed. This is exactly what broke our naive implementation. Right now the data is sitting in the producer CPU cache, that is the store buffer. It hasn't necessarily flushed to RAM. If we updated the tail index right now, the consumer might wake up, see the next index, but read garbage data because this A hasn't yet arrived yet. So how do we fix it? Here is the fix. We use the release barrier. We are about to update tail to publish the record. We use store release. Unlike the mutex which stops the world, release acts like a barrier. It forces all pending data to flush into the main memory before the tail variable is allowed to change. It enforces the order, data first, index second. Now the tail updates to 1. Because of that release flush, we have a contract. The data now is visible at the index 1. You cannot see the index without also being able to see the data. Now let's jump to the consumer. It wakes up and checks its own head index. Again relaxed, ordering is fine here, it's local data. Now the consumer checks tail to see if there is work to do. In the mutex version, we would acquire a lock here. But in this version, we use an acquire barrier on tail. This shield works with the producer's release. It invalidates the consumer's local cache. It says if you see the tail has moved to 1, you are also required to accept all the data flushes that happened before that move. This makes sense, right? This ensures we never read the ghost version of the data. We never read the stale data. So because of that acquire release handshake, the data is solid and up to date. We copy it out safely. Finally, we update head using release to tell the producer the slot is free. This is the standard pattern for lock-free programming. Data is the payload, the atomic variable is the signal, and the barriers ensure they arrive in right order. I want you to burn this image into your mind. This is lock-free pattern. We have a payload here. This is your buffer data. It is physically just bytes in RAM, but to the rest of the world, it's an invisible data. The signal on the right, this is your atomic variable, head or tail. It acts like a flag. The barriers, these are the acquire and release commands. They are the glue. If you change the signal without the barrier, the payload arrives late and your code crashes. But if you use the barrier, you guarantee that whenever the signal is raised, the payload is already waiting. Okay, now let's dive into the code. Let's see how the atomics work and how we achieve a performative and safe SPSC queue. So now let's walk through the actual C++ implementation. Structurally, nothing has changed. We still have a fixed size string buffer, head index, tail index as usual. The only difference is how synchronization is done. Instead of the mutex, we now have atomic. This works because of a key constraint. Only the producer ever writes tail and only the consumer ever writes head. That single write property lets us avoid more expensive synchronization. So let's start with the enqueue operation. We load the current tail using the memory order relax. This is safe because, as I already explained, only the producer writes head. We don't need ordering here, just the value. Now we do the full check. We check whether the queue is full. We compare against head. This load uses the memory order acquire. That acquire load guarantees we see the most recent head that is released from the consumer, along with all the memory effects that happened before it. So this is the key part here. And then as usual we do the memory write, but what matters is what happens after this. Here we have tail.store and we are using memory order release. This release store is the key. It guarantees that the buffer write happens before the updated tail becomes visible to the consumer. So here we are achieving the synchronization. Without this, the consumer could observe the new tail value and read stale or uninitialized data. That's exactly the failure mode we saw earlier in the naive version. So we are fixing it using the acquire release synchronization pair. I hope that makes sense. Now similarly moving to the DQ operation, we do the same load using the memory order relax as consumer is the only one updating the head, and then we do the empty check, and here we do the memory order acquire. This pairs with the producer's memory order release and guarantees we see the updated tail. We also see the buffer write that happened before it. So as soon as the memory order release kicks in, the memory order acquire sees the updated buffer data as well as the updated tail. And similarly then we do the head store using the memory order release, and it makes sure that the producer sees the updated head value. And similarly we do the empty check using the relaxed and the memory order require. Here notice that we use head as memory order relaxed because we do the empty check only in the consumer. So for the consumer the head is only updated by itself, so we don't need like a overhead synchronization of doing released or acquire. So we have used relaxed, and similarly the tail we do the acquire on it. And then the standard we run the thread producer consumer as we have already seen. Okay, now let's execute the code. I've already compiled it. I'll execute it. So you can see there are no lost values, no duplicate values, no hangs. We'll execute it again to make sure it works perfect. Yeah, you can see again there is no lost value, no duplicate. So we have achieved the synchronization which we were looking for. But you might have noticed, unlike the mutex version, there is no blocking or no context switching. So this version is faster and non-blocking, but it comes at the cost. The code is harder to reason about, easier to get subtly wrong, very sensitive to memory ordering mistakes. This is why lock-free code should always be built on top of known correct baseline, as we have done. We have created the correct baseline using the mutexes, and then on top of it, we create a lock-free version of it using the atomics. That's the end of the full SPSC queue journey. We have seen the naive implementation, correctness using the mutexes, lock-free implementation with atomics, same queue, same logic, different synchronization. That's the complete journey. If you followed around through the details, thanks for sticking with the scene. Please subscribe, share and like. See you in the next one.